The last section of this chapter that we'll be discussing will be the fourth section, which is on changes of state. So let me remind you, anything that I haven't covered in this chapter is not going to be covered on the test. Okay? All right, as far as changes of state goes, let's talk about changes of state in equilibrium. All right, if we talk about just evaporation, so if we think about evaporating water, first of all, where does it occur? Evaporation, first of all, only occurs at the surface of the liquid, so where you have the interface of the uh, uh, air and the liquid, that's where the evaporation occurs. The first thing is that you need to have particles that have enough energy in the liquid phase to overcome the attractive forces of the hydrogen bonding, which we've already discussed hydrogen bonding. So and we're talking about water. So hydrogen bonding is a pretty significant force of attraction between polar molecules, and you need to have stuff that is moving fast enough in order to do this. Well, if you remember, only the stuff at the extreme level of a bell curve is going to have enough energy to evaporate. So in other words, this is number of particles and this is the amount of energy that they have, if I have this, only the extreme top portion of this, a number of particles, has enough energy to evaporate. So just this top portion right here, okay? This is about 25 degrees Celsius water, let's say. So only this extreme stuff here is going to be available to evaporate. So what conditions are necessary for condensation to occur? Again, I have to have now particles that are moving slow enough. So particles that are moving slow enough to your Coke can, in other words, not at 25 degrees Celsius, but now we're looking at really slow temperatures here, or really low temperatures. So the particles slow down enough to condense on your Coke can or your glass of ice water or something like that. Okay, so loss of kinetic energy, usually through temperature, is the way that these things work. All right, so a phase is a part of a system with uniform composition and properties. So we're talking about the gas phase, or the liquid phase, or the solid phase. And equilibrium is a dynamic condition. So dynamic means it's constantly moving, it's constantly becoming something, it's in a state of flux. And here I have two opposing conditions. So two opposing conditions. So these opposing conditions could be condensation versus evaporation. So they're opposing each other at equal rates in a closed system. So I got to put a cap on it. That's a closed system, and they're occurring at equal rates or at the same, I guess, the same rate. One is happening at the same rate as the other. So here I have a definition: equilibrium vapor pressure is the pressure exerted by a vapor in an equilibrium with its corresponding liquid at a given temperature. What this basically means is that at a given temperature is a very important statement. So let me highlight that. Let's say at 25 degrees Celsius, I have a capped liquid, let's say it's water. It's going to establish, over time, it's going to establish what's called an equilibrium vapor pressure. In other words, initially, we're going to have a lot of evaporation, and over time, the two opposing forces of evaporation and condensation will be in equilibrium. They're happening at equal rates. And lastly, they are going to be this sets up this equilibrium vapor pressure. So there's gas above the liquid. So what happens when temperature is increased? We'll talk about that on the next slide. I obviously give you the answer here. As kinetic energy increases, vapor pressure increases, and equilibrium vapor pressure is established at a higher temperature. So as kinetic energy increases, vapor pressure increases. Okay, as kinetic energy decreases, vapor pressure decreases. So what we have on this slide is we have an uncapped system. You'll notice it's uncapped up here. Okay, so no cap. And so we have a lot of evaporation and very little condensation. So we have more arrows going up than we have down. Well, here it's capped. So once you put a cap on it, you have equal amounts of condensation, so arrows going down, and equal amounts of evaporation, or arrows going up. So over time, this is giving us an equilibrium vapor pressure. So there's a certain pressure being exerted by these particles against the sides of the container and the surface of the liquid. Okay? If I increase the temperature, I obviously have increase in evaporation, so it'll reestablish the vapor pressure at a different point. All right, next. All right, vapor pressure and equilibrium vapor pressure are specific to every liquid. Now, why is this? Every liquid has different properties. They could be physical properties, chemical properties, but let's talk about the physical properties. The biggest thing that we see is that every liquid has its own specific attractive forces. In other words, hydrogen bonding, dipole-dipole forces, and so on and so forth. Without reviewing all those types of forces, let's just talk about if there are strong attractions. And this is, again, hydrogen bonding, strong dipole-dipole forces. You're going to have low evaporation and low vapor pressure. Okay, so strong attractive forces means the particles are really attracted to one another, and they'd rather stay in the liquid phase, so you're going to have a low rate of evaporation with low vapor pressure. If you have weak attractions, then the particles aren't so sticky. They now detach from each other and they have a high evaporation rate. And if you have a lot of evaporation, then you must have a high vapor pressure. Okay? And these things, these weak attractions are called volatile liquids. And everyone thinks volatility is the amount of how much it'll explode. It's related, but in this case, volatile is just liquids that readily evaporate due to weak attractive forces. So volatile liquids will have high evaporation rates and high vapor pressures. Okay? Now, what about boiling? Everyone thinks, and I did too, that boiling has to do with temperature, but it really doesn't. Boiling is a change of state within the liquid at the surface. And the boiling point is the point at which equilibrium vapor pressure and atmospheric pressure are equal. Okay. So notice there's no mention, it's the point, it doesn't necessarily have to be temperature, but it's this point in which the equilibrium vapor pressure and atmospheric pressure are equal. So equilibrium vapor pressure is the pressure pushing down, equilibrium vapor pressure is the pressure coming up off the liquid, and atmospheric pressure is the pressure that's trying to subdue it. So when these two things are equal, I have boiling. It just so happens that to get to this point, I have to raise the temperature. Okay, let me give you a fresh slide and let me discuss this. All right, if I have a liquid, that's a beaker. If I have a liquid, and here's my liquid, okay, I have 1 atmosphere of pressure pushing down on this liquid, okay? That's standard atmospheric pressure, which we'll talk about in Chapter 11. But this might only be pushing up by 0.1 atmospheres. In other words, the vapor pressure coming up off the liquid's very, very weak. So how do I get this vapor pressure to be more? Well, I heat it up. If I heat it up and get it to 100 degrees Celsius, obviously that's the boiling point of water at standard atmospheric pressure. But I do know that at this temperature, I have a lot of particle movement. So the particles are moving like crazy. And as they're moving around and jostling, I have even more vapor pressure. So if I have more vapor pressure, now this 0.1 atmospheres at higher temperature goes up. Instead of being 0.1 atmospheres, it's 0.5 atmospheres, it's 0.6, it's 0.7. Finally, it's 1 atmosphere. And when 1 atmosphere is coming up off the liquid, 1 atmosphere, then that's going to equal the 1 atmosphere pushing down. I have boiling. So the two pressures due to gases have to be equal. The pressure coming up and the pressure going down. Okay? When I have that, I have boiling. Okay? Now, this is some vapor pressure and boiling. You'll notice, by the way, this line right here is 1 atmosphere or standard atmospheric pressure. Okay, again, we haven't talked about that just yet, but we will. And you'll notice that here I have water, ethanol, and diethyl ether. And you notice they all boil at different temperatures. Okay? So what must I conclude about this? Well, I must say that water, since it has the highest boiling point, must also have the highest intermolecular forces because the particles are super sticky, so I have to get the temperature higher in order to make these things boil. The diethyl ether must have the weakest intermolecular forces. This is more of a volatile liquid. This is not so much a volatile liquid, and therefore lesser temperatures are needed to boil diethyl ether. Okay, because the particles have weaker intermolecular forces. Okay, The temperature of a boiling liquid and its resultant vapor pressure, vapor are equal. If we continue to apply heat, why doesn't the temperature of the water vapor increase as well? Okay, have you ever wondered that? Why water boils at 100 degrees and never gets any hotter, like in your kitchen? And the answer is this. Any type of additional energy that's applied, in other words, you keep heating it up, is used to break the attractive forces of the liquid phase. So any additional energy that you're trying to apply to a liquid, the liquid, such as water, cannot boil above 100 degrees Celsius because any of the additional energy going in is not trying to make the particles move faster. It's trying to break the forces of attraction at the surface. That's where the energy is going. Okay, it has to do with potential energy as well, but we're going to ignore that for now. Okay, molar enthalpy of vaporization. I don't understand what's... Okay, there we go. All right, molar enthalpy of vaporization, or delta HV. And by the way, enthalpy is just a fancy word for heat, and I won't discuss why at this point. I don't think we need to know that. But molar heat of vaporization, or molar enthalpy of vaporization, is the amount of heat needed to vaporize 1 mole of a liquid at the liquid's boiling point at constant pressure. Now, every liquid has its own molar enthalpy of vaporization. It's a physical property. This value is specific to every liquid. Okay, so this is a value that I have to actually look up. The higher the molar enthalpy of vaporization, the stronger the strength of attractive forces. The weaker or the lesser the molar enthalpy of vaporization, or the lower that number is, the weaker the strength of the attractive forces. Freezing. As far as freezing goes, freezing is basically just taking a liquid and removing energy. So this is actually called an exothermic process. Whenever energy, notice energy is on the right side of the arrow, so it's a product. And if it's a product, that means that energy is being removed. And this is an exothermic process. And how do I know that? It has to do with your freezer in your house. If you'll notice that your freezer, there's always warm air coming off the exhaust of that. Well, it comes from a couple different places. The motor, yes. But the biggest place that this energy is coming from is the removal of energy to make ice. See, I have to remove energy from water to make ice. So in order to go from a liquid to a solid, I have to take the energy out. And when I take energy out, it's got to go somewhere. Well, your refrigerator removes that as this extra heat, and you kind of feel that down by your toes in the morning when you're getting your bowl of Wheaties together or whatever you eat. But anyway, the freezing point is the temperature at which the solid and the liquid are in equilibrium at 1 atmosphere. So again, same definition, but this is where the solid and the liquid are at equilibrium. So at 0 degrees Celsius for water, I can have a glass of water, and if I had a carefully controlled refrigerator, and I took a glass of water, so here's my glass of water, and I have ice cubes in there, and I put it in a 0 degrees Celsius refrigerator, this ice would not melt, and nor would the water freeze. It would stay like this forever and ever. Okay? If I raise the temperature just a little bit, all the ice melts. If I lower the temperature just a little bit from 0 degrees Celsius lower, then all the water freezes. But at its freezing point, I have an equilibrium of water and water and ice. Okay, so at freezing point, solids and liquids have the same kinetic energy, therefore energy loss is in the form of potential energy. And what's happening here, the particles are gaining order, and the temperature stays constant until all the freezing is done. And of course, melting is now, you'll notice I'm adding energy to get a liquid. So here energy was a reactant, here energy is a product. Okay, so two opposite forces, or two opposing things. All right, freezing and melting. If I have pure crystalline solids, freezing and melting occur at the same temperature. At standard pressure, if solid and liquid exist simultaneously, then the temperature of the system remains constant. Temperature will change when either phase changes complete. Example, heat up in ice water mixture, what happens to temperature? I think I've already discussed this. Okay? Now, the molar enthalpy of fusion is the amount of heat required to melt 1 mole of solid at the solid's melting point. So this is the amount of energy it takes for to melt one solid at its freezing point. And again, this has to do with the strength of intermolecular forces, and it has to be specific to each solid. So whatever we discussed with molar enthalpy of vaporization, applies to molar enthalpy of fusion, but opposite because we're dealing with an opposite type of transformation. Sublimation and deposition. Sublimation is where I'm going to take a solid, I will add energy to get a vapor. So the solid goes directly to a gas. This has to do with dry ice or CO2. And deposition is where the vapor goes directly to a solid and energy is removed. This is frost on your windshield in the morning. So that gas is deposited directly as a solid ice and skips the liquid phase. The last thing that we're going to talk about is something called a phase diagram, and this is the phase diagram for water. And a phase diagram shows how all three phases are in equilibrium with each other along the lines. So you notice a solid is in equilibrium with a liquid along this line, the liquid is in equilibrium with the gas along this line, and the solid and the gas are in equilibrium along this line. Which brings me to this point right here. It's called a triple point. And this is a point, and it's one point for every phase, or every substance, to my knowledge, where all three phases, solid, liquid, and gas, are in equilibrium with each other. So that's the triple point. Okay, another thing is called the normal melting point, normal freezing point, or the normal boiling point. This all happens at 1 atmosphere. So this has to happen at 1 atmosphere, and this is where a substance will freeze at 1 atmosphere, the temperature at which a substance will freeze at 1 atmosphere, and the temperature at which a substance will boil at 1 atmosphere. Okay? And then the critical point here is the highest point. It's solid, where a liquid or a gas can no longer exist at the temperature and pressure that's listed. And that's it. Okay. Realize this was the longest one. If you guys have any questions, come see me. That's it.